All right, it's December. Welcome back to the next day of versions. Hope you all have a nice, relaxing time. You're ready to make it through these last 2 weeks. There's really only kind of one thing left to talk about, to be perfectly honest, but there's a few things to build it up. So let's we're still working in the realm of eigenvalues and eigenvectors. So, and I will say, and I've said this already a few times, I'll say it again. If you're taking 17C, you definitely need to know how to find the eigenvalues and eigenvectors of a 2x2 matrix and to understand kind of what they are. So let's kind of talk about some questions you could see. For example, let's say someone asked you this: is lambda equal to 3 an eigenvalue of this matrix? 1, 2, 2, 1. So the question isn't how do we answer this question? The question is, what's the fastest way to answer this question? Because you could certainly try to answer this question by finding the eigenvalues of the matrix, but that's not the fastest way to do this question. So here's how you should solve this. So the easiest way to see this is to ask yourself, is the determinant of A minus lambda I equal to 0? Because if it is, then it is. And if it isn't, then it isn't. So instead of doing the determinant of A minus lambda I and setting it equals 0 and solving that quadratic equation, we're going to just plug in 3 for our lambda and ask ourselves, okay, is the determinant of our matrix 1, 2, 2, 1 minus 3 times our identity matrix 1, 0, 0, 1. And again, I think you can skip this step, right? You know what you're just subtracting 3 from each diagonal. I'm showing my work. So the question is, this determinant of 1 minus 3, 2, 2, and 1 minus 3, does this equal 0? And the answer is yes, right? Here the determinant is going to be -2 times -2 minus 2 times 2. And that is equal to 4 minus 4, which is 0. So 3 is an eigenvalue because the determinant of a minus lambda I is equal to 0. I should say the determinant of a minus 3I is equal to 0. There are other ways to solve this, but this is kind of the most efficient way to do it. If someone's just asking you is this an eigenvalue, don't try to find all the eigenvalues. Try to just check that one. There is another eigenvalue here too that I don't know what it is, and I don't care. Right? That's not what the question was asking me. You might say, well, okay, that seems relatively not too terrible for this, but it gets to be a little bit more interesting if we have larger matrices. So for example, yeah, let's just have a feature. We could ask the next question in a similar sort of way. Is lambda equal to 0 an eigenvalue of this matrix? B equal to 0, 2, 1, 2, 1, 0, 0, 2, 1. And especially here, in the situation where we have a 3 by 3 matrix and we don't really have all the tools, like not that we don't know the kind of process we're doing, but it's much more challenging if your matrix is 3 by 3. Sometimes it's really, really challenging to find the eigenvalues. We shouldn't be trying to find the eigenvalues here. I don't care what the other two are. I just care, is 0 one of them? So we're going to check. Okay, I'm going to look at the determinant of my matrix minus lambda times I. And in this case, lambda is 0. So lambda times I, that's just the 0 matrix. So really, I'm just looking at the determinant of my matrix B, and I'm asking the question, is this equal to 0? Let's find out. So let's see. So for a 3 by 3, we have this special way of doing it. You write down your matrix, and then you write down the first two columns again. So 0, 2, 0, 2, 1, 2. And then we do the thing, right? So let's see. So let's do this kind of quickly. So to find the determinant of B, we're going to say it's equal to, let's see, 0 times 1 times 1 is 0. 2 times 0 times 0 is 0. 1 times 2 times 2 is 4. Minus 1 times 1 times 0 is 0. 0 times 0 times 2 is 0. 2 times 2 times 1 is 4. So yeah, those are going to subtract to 0. So yes, 0 is an eigenvalue of this matrix. All right, your turn. Is lambda equal to 3 an eigenvalue of A equal to 5, 2, 3, 1? Oops. All right, what do we think? Yay or nay? Well, I see mostly nays. Let's check. So let's see. So I'm doing my determinant of my matrix minus lambda I, and I'm getting the determinant of 2, 2, 3, 2. It's looking bad. That's going to be 4 minus 6, which is not 0. So no, lambda equal to 3 is not an eigenvalue. Yeah, question. Thank you so much. It is. So 2 times -2 is -4 minus 6, which is not -2, it's -10. Still not an eigenvalue, but good to have the correct calculation there. Okay, one more, actually two more because I want to point something out. So we could ask, is lambda equal to -5 an eigenvalue of a equal to 2, 3, 0, 4? In this instance, I don't think you need to do really any work because that matrix, we should all be able to say what the eigenvalues are without doing any work at all. The answer here is no. We already know the eigenvalues. The eigenvalues are 2 and 4. And we know that they're 2 and 4 because we have an upper triangular matrix here. So this matrix having a 0, I should say having all zeros below the main diagonal is upper triangular. And if that's the case, your eigenvalues are always, always, always going to be the diagonal entries. In case you're not sure, here's why. If I was trying to find the eigenvalues, I would say the determinant of a minus lambda I, well, that's going to be the determinant of, check it out, 2 minus lambda, 3, 0, 4 minus lambda. And when you actually take the determinant here, look what you get. You get 2 minus lambda times 4 minus lambda minus 0, right? 3 times 0 is 0. Minus 0 doesn't change anything. So I'm not even going to write it. I'll write it down. But really, what you should be writing is just 2 minus lambda times 4 minus lambda is 0. It's already factored for you. You already know what the eigenvalues are. They're +4 and +2. So if you see a matrix that looks like this, or I'll just say this matrix here, 2, 0, 3, 4, this matrix here that is lower triangular, you're going to have the exact same thing happen because your determinant of a minus lambda I is going to be 2 minus lambda times 4 minus lambda minus 0 again. So if you ever have a 0 up here or a 0 down there, your eigenvalues are going to be the diagonal entries. That idea is actually extendable to larger matrices. What do I mean by that? Well, let me show you. So instead of asking the question this way, I'll just say what I really want to say, which is this. What are the eigenvalues of the matrix A equal to, sure, let's do it this way, 2, 0, 0, 3, 5, 1, 2, -4, -6. Oops, that's a 0. That's a 0. Apologies. Otherwise, it's not going to work. So, so here's a matrix that is also lower triangular, right? Everything above the main diagonal is 0. And in a matrix like this, you automatically get to know what the eigenvalues are. Here, the eigenvalues are +2, +5, and -6. We could even show the work. In fact, let's go ahead and do it. You don't need to write this down necessarily, but if we were asked to find them, usually for a 3x3 matrix, it's pretty hard. But if you have one that's lower triangular like this or upper triangular where it's all zeros below the main diagonal, it's really, really easy. Here's why. If we look at the determinant of a minus lambda I, check it out. It's going to be the determinant of 2 minus lambda, 0, 0, 3, 5 minus lambda, 0, 2, -4, -6 minus lambda. And to do that, I'm going to do the thing we usually do for 3x3s. I'm going to copy down the first two columns. It's kind of a lot. 2 minus lambda, 3, 2, 0, 5 minus lambda, -4. But now look what happens when I multiply this all out. It's going to be that plus that plus that, but the second two things are zeros. So it's just 2 minus lambda times 5 minus lambda times -6 minus lambda minus 0 plus 0 plus 0. Oh, look, it's already factored for us. So my eigenvalues have to be lambda equal to +2, lambda equal to +5, and lambda equal to -6. And the reason why I'm kind of spending a few minutes emphasizing this is because it actually does come up with some frequency, right? Like when you're on your final exam, there'll probably be a matrix or two where it is upper or lower triangular, and it's going to be super, super easy to see what the eigenvalues are. Maybe, but definitely in 17C, enough of the time you will see matrices like this that it's worth, like, oh yeah, I know what those are. I don't have to spend the time thinking about what they are. A harder question to answer, a question that requires a little bit more work, is if a vector is an eigenvector of a matrix. But again, still, we don't really want to do all of the work one would have to do to find all of the eigenvalues and eigenvectors. So, let's take a focus here. Let's look at this question. Yeah, we'll start there. So here's a question that's interesting to ask. Is this vector 2, 1, 1 an eigenvector of, there's no O in eigenvector there, of this matrix? -3, -1, 5, -2, 1, 2, -2, -1, 4. And even if we could find the eigenvalues and eigenvectors of that matrix, that's a lot of work, right? It's way easier to check to see if this is an eigenvector by checking the following. So I'll remind you, to be an eigenvector, it means that the matrix times the vector equals a multiple of the vector. So the question we're really asking is it true that, let's call this matrix A here, that A times our vector is equal to a multiple of our vector? That's what we're really trying to figure out. So all we're going to do is multiply our matrix by our vector and see if we end up getting a vector that happens to be a multiple of it. Let's check. So let's see. So our matrix A is -3, -1, 5, -2, 1, 2, -2, -1, 4. We're multiplying it by the vector 2, 1, 1. So usual stuff. See, we're going to get -6 minus 1 plus 5. See, -6 minus 1 is -7 plus 5 is -2. And then we're going to get -4 plus 1 is -3 plus 2 is -1. And we're going to get -4 minus 1 is -5 plus 4 is -1. And yeah, that's looking good. That exactly looks like a multiple of this vector. In fact, we should write it as -1 times our original vector, 2, 1, 1. So the answer is yes. 2, 1, 1 is an eigenvector of that matrix. You can't just say a vector is an eigenvector blanket. It has to be an eigenvector of a particular matrix. Anyone want to volunteer to tell me what the eigenvalue was for that eigenvector? Thank you. Yes. -1, right? Whatever the multiplier is, that's the associated eigenvalue. So there's your eigenvalue that goes with this eigenvector. Let me grab another one here. Sure. 1 second. Yeah. So, papers. One. Yeah. Sure. Why don't you all try this one? So same question. Your matrix is -9, 4, 6, -6, 3, 4, -9, 4, 6. And your vector is 2, 0, 3. So the question is V an eigenvector of A? Find out. Let's see. We multiply this matrix by this proposed eigenvector. What do we get? See, negative 18 plus 0 plus 18 is 0. Negative 12 plus 0 plus 12 is 0. Uh-oh. Negative 18 plus 0 plus 12 plus 18 is also 0. Does that mean it's an eigenvector? Is this vector equal to some multiple of your original vector? What number could you multiply this vector by and get that vector? Yeah. And 0 is okay for an eigenvalue, just not for an eigenvector. So yes, this is an eigenvector. V equal to 203 is an eigenvector, and the eigenvalue is 0. It's kind of neat. Okay, one more because there's one more I have that I want to show you. This is the following one, which is going to be kind of funky, but good to start thinking about now. So is the vector 2, 2i an eigenvector of the matrix 1, 2, negative 2, 1? Ooh, imaginary numbers. Okay, so let's do it. So we take our matrix times our vector. We get 1, 2, negative 2, 1 times the vector 2, 2i. We multiply that, we get 1 times 2 plus 2 times 2i is 4i. And then negative 2 times 2 and 1 times 2i. So now here's the question. Is this some number times 2, 2i? This one always feels like it's a little hard to figure out. Because like in the previous ones, it's like, well, it's, it was negative 1 or 0, and obvious, like you multiply this by that to get that. So here's how you can check this one relatively easily. In your eigenvector, or your supposed eigenvector, look for the thing that doesn't have any i's in it, if there is one. So I'm looking at that 2 there, and I'm going to ask, okay, what would lambda need to be so that lambda times 2 was equal to 2 plus 4i? Well, let's write that down. Lambda times 2 equals 2 plus 4i. If I divide both sides by 2, lambda would have had to have been 1 plus 2i. So then the question is, if lambda is 1 plus 2i, am I going to get the bottom part right? Let's find out. So 1 plus 2i times 2, 2i. We know the top part's going to be 2 plus 4i. The bottom part's going to be, let's see, 1 times 2i, and 2i times 2i is 4i squared, but I squared is negative 1. So yeah, this works. We get 2 plus 4i, and we get 4 times negative 1, which is negative 4 plus 2i. So yeah, the answer is a deafening yes here. Our vector 2, 2i is an eigenvector, and the eigenvalue is complex. The eigenvalue is 1 plus 2i. I'll remind you, you're probably not going to see much, if any, of this in this class, but again, 17C, you will certainly see complex eigenvalues. Like, for sure, without a doubt, for sure. Okay. So now where do I want to go with this here? Let's take a look real quick. Yeah, that's where we're going to go. Sure. Okay, so one thing we can do with eigenvalues and eigenvectors is simplify the process of repeated matrix multiplication. So let me back up a little bit. Let me provide some framework here. So here's where we're going. Okay, move out of the way here. So suppose we're going back to Leslie matrices. Suppose we are studying a population divided into 2 age classes. Juveniles and adults. Juveniles have an average of 2 offspring, while adults have an average of 6. 50% of juveniles move on to become adults. Here's the Leslie matrix. So the Leslie matrix looks like this. Let's see, it should be a 2 and a 6, and a 1/2 and a 0. And again, I'm not really great at coming up with the Leslie matrix without actually thinking about the multiplication. So what I'm really thinking about here is writing down like this Leslie matrix times this year's juveniles, right this way, yeah, and this year's adults. When I multiply this out, check what I get. I get 2 times this year's juveniles plus 6 times this year's adults. That's going to be next year's juveniles, or next whatever time period we're talking about, it's juveniles. And then 1/2 times JAT plus 0 times AT, that's going to be next year's adults. Okay, things are working out the way the words say they should, right? 50% of juveniles move on to adulthood. I guess it didn't really say anything about how many adults survive, but like, okay, whatever. Sometimes the words are not perfect. So great, there's my Leslie matrix. So now we're going to ask some questions. So if we are given an initial population of J sub 0, A sub 0 equal to 180 respectively. So 100 juveniles at time 0 and 80 adults at time 0. How many juveniles and adults at time 1? Okay, well, that's just taking the vector we're given and multiplying it by the matrix. So our J1A1 is going to be our matrix 2, 6, 1/2, 0 times our J0A0, which is 180. So what do we get? We get 2 times 100 plus 6 times 80. So 200 plus 480. And then 1/2 times 100, which is 50. So we get, let's see, what, 680 and 50. Okay. And then what if we asked about next year, the year after that, after 2 years or 2 time iterations? Well, then we multiply again, which is going to start to feel kind of terrible. What about t equal to 2? Well, J2A2 is going to be our matrix 2, 6, 1/2, 0 times our J1A1 there, which is 680 and 50. And then we do the same math. It's going to be 2 times that plus 6 times that. So, yeesh, 1,360 plus 6 times 50 is 300. And then 1/2 times 680 is 340. And as you can kind of maybe start to guess, the math gets a little bit gross. Right? What if I said, what about 30 years from now? I don't want to do this 28 more times. None of us want to do this 28 more times. Obviously, a computer could do this really easily 28 more times. But we're pretending like, I don't know, we don't have access to computers or something. Some of these questions always seem a little bit like, we could do this really easily with all of the tools humanity has. But it is about learning how it works, not about actually doing it. So the question is, how do we find out what a to the 30th power times our a naught? I meant to call it L. Apologies. Terrible. That's terrible, James. how do I figure out what L to the 30th power times our A naught J naught vector is going to equal? And usually we call this vector here lowercase n naught. So really we're asking, how do we calculate our matrix raised to a really high power times our initial population vector? And actually 30 is just kind of a whatever number. We really are asking how to calculate our matrix raised to any power, any choice of time times our initial vector. That's what we're really interested in. So the process is lengthy. And there's kind of two different equally good ways of thinking about it. So I'm going to try and show you the way I think is easier to comprehend first, and then we can talk about the other way. But they both work. So yeah. How much do I want to show here? Sure, let's do the whole thing. So we're going to go very kind of generic first. So we'll talk about the process, and then we'll come back around to this example in a few minutes. So let's just use the whole piece of paper, James. Don't be stingy. Okay. So here's the idea. Let's assume we have a 2x2 matrix, and we found the eigenvalues and eigenvectors with eigenvalues lambda 1 and lambda 2, and associated eigenvectors v1 and v2. And here's what we know. We know that for either eigenvalue and eigenvector, that our matrix, I'm going to call it A because that's pretty standard, that A times our eigenvector is equal to the eigenvalue times the eigenvector, whether it's lambda 1 and v1 or lambda 2 and v2, right? This is the relationship we have. So then, instead of trying to write both of those equations at once, right? A times v1 equals lambda 1 times v1, and A times v2 equals lambda 2 times v2. I'm going to want to write both of those equations in one kind of matrix equation. Here's how that's going to work. We're going to let P be the matrix whose columns are eigenvectors. So the first column is the first eigenvector. The second column is the second eigenvector. It literally does not matter which one you write first or second, as long as you know which one you've written first or second, and that the other things correspond later on. Don't worry, I'll say more. So often we write notation like this, where you're kind of like, okay, V1 is the entire first column, V2 is the entire second column. So then, look at this equation. We're going to say that our A times P, well, that's really A times V1 and V2. This matrix, you can think of it hitting V1 first. A times V1 should be lambda 1 times V1. So this is really going to equal lambda 1 times V1 in your first column. And similarly, the A times the second column here is going to equal lambda 2 times V2 in your second column. You can really just imagine doing each one separately, right? Literally, if you multiply the matrix A times the vector V1, you get the vector lambda 1 times V1. If you multiply the matrix A times V2, you get the vector lambda 2 times V2. And there are both columns, all columns here. So the matrix multiplication really does work out. Now, the next step here is where I used to get flipped around, but it's not impossible to see. You just have to be a little bit visually smart here. To me, this always feels kind of wonky, but we're going to write this as, James, you're going to write it wrong. You're going to write it as the vector V1, vector V2 as a matrix, times the matrix of eigenvalues, lambda 1, 0, 0, lambda 2. This part always felt a little bit like, really, James? But yeah, it totally works, right? If you have, in fact, I'm going to show you over here so you can, I always feel like if I had these two matrices, sure, I don't really love this. But let's say I had something like, 3 times the vector 1, 2, and 2 times the vector 5, 7, which would actually look like the matrix 3, 6, 10, 14. I could totally write that as the matrix 1, 2. I know I'm saying it in kind of the opposite order I usually do. 5, 7 times 3, 0, 0, 2. If you do that multiplication, it totally works out. 1 times 3 plus 5 times 0 gives you the 3 there. 1 times 0 plus 5 times 2 gives you the 10 there. 2 times 3 plus 7 times 0 gives you the 6 there. And 2 times 0 plus 7 times 2 gives you the 14 there. So really just kind of work to say, oh yeah, whatever these eigenvalues times these eigenvectors are, you can kind of pull off the eigenvalues and put them in their own little matrix here. Your own little diagonal matrix here. So what ends up happening here is we end up getting that this is our matrix A times P equals P times the matrix that we call D. D for diagonal. This is a diagonal matrix, and the diagonal entries are exactly the eigenvalues in the same order that we wrote the eigenvectors. So that's why if V1's first and V2 is second, then lambda 1 is in the first column and lambda 2 is in the second column. So it's kind of a lot, I know. Don't worry, we're almost there. So check this out. If I want to isolate A, I'm going to multiply both sides on the right by the inverse of P. Fun fact, P is always invertible because the eigenvectors are not multiples of each other. They can't be. There's all sorts of stuff about how P works out just fine. So don't worry about whether or not P inverse exists. It does. So we're going to say that A times P inverse equals P times D times P inverse. Why did we do that? What's P times P inverse? The identity, right? That's why right? That's the very definition of being an inverse, is that the two inverse matrices multiply to the identity matrix. So that's the identity, and then A times the identity is just A. So check it out. We've rewritten the matrix A as P times the diagonal matrix times P inverse. And you might be thinking, well, this seems like not all that useful yet, but it is. Here's why it's useful. This matrix over here is much, much, much easier to raise to a very, very high power. What do I mean by that? Well, if I look at, for example, A squared. Well, again, A squared is just PDP inverse squared. And when you square something, you just multiply it by itself. So look what happens. We get PDP inverse times PDP inverse. But in the middle, we have P inverse times P, which is the identity matrix. So this really becomes P times D times the identity matrix times D times P inverse. I don't care about the identity matrix. It's not changing anything. Let's multiply by 1. So I have P times D times D times P inverse, or P times D squared. And diagonal matrices raised to higher powers are easy to calculate. D squared is super duper easy here. D squared is just lambda 1, 0, 0, lambda 2 times lambda 1, 0, 0, lambda 2. That's going to be lambda 1 times lambda 1 plus, let's see, 0 plus 0, 0 plus 0, and 0 plus lambda 2 squared. Or as we saw before when we talked about this, when you raise a diagonal matrix to a higher power, you just raise each of the diagonal entries to that higher power. That is not typically true for matrices, but it is true for diagonal matrices. So it makes them really, really nice. So you could kind of go on this way and say, well, great. More generally, if you want to raise A to any power, A to the T is going to equal PDP inverse to the Tth power. You're going to write that out a bunch of times. How many times? T times. And look what happens. Every P inverse times P in the middle is going to become the identity, which means its multiplication is kind of not essential. and you just get P times D times D times D times D times D times D times P inverse. Or in other words, you get P times D to the power of T times P inverse. Meaning it's really, really easy to calculate A to some high power. Not really, really easy. Relatively, comparatively easier than trying to, do it with just your original matrix A, not transformed this way. So, back to what we were saying before. So, actually, one more thing. So, just more generally, we can say that your n sub t, which is your initial population multiplied by your matrix A t times, that's going to be your A to the t times n naught. It's going to be much, much easier to think of that as P times D to the t times P inverse times n naught. So back to our previous example. We had our matrix was 2, 6, 1/2, 0. I know I just started calling it A, will live. And we had n naught equal to 180. And we wanted to find n30, right? We wanted to find A to the 30th power times n naught. Do that, we're going to take our matrix, find the eigenvalues, find the eigenvectors, find the matrix P and the matrix P inverse, and then do this calculation, which still is quite a bit of work, but it's less terrible than actually trying to multiply A by itself 30 times, like orders of magnitude less terrible. So let's do it. All right, so I don't have a 0 in the nice spot, so that means I actually have to do the work to find the eigenvalues. So eigenvalues. Determinant of or A minus lambda I, that's 2 minus lambda, 6, 1/2, 0 minus lambda, or just negative lambda if you prefer. That's going to be 2 minus lambda times negative lambda minus 6 times 1/2 is 3 equal to 0. Multiplying this out, negative lambda times negative lambda is lambda squared. Negative lambda times 2 is minus 2 lambda minus 3 equals 0. Hopefully it factors. It does. It factors as lambda minus 3 times lambda plus 1. So our eigenvalues are lambda equal to 3, lambda equal to negative 1. Then we find the eigenvectors. We can move the paper. So the eigenvectors. By the way, part of this whole explanation is why I really like to think about the eigenvector equation is A times your vector equal to lambda times your vector instead of A minus lambda I times your vector equal to 0. To me, that just makes more sense. So that's why when I'm trying to find my eigenvectors, I'm going to say this is lambda 1, this is lambda 2. I'm trying to solve my matrix times my unknown eigenvector equal to my eigenvalue times my unknown eigenvector. That's what we're trying to do. So my matrix is 2, 6, 1/2, 0. We don't know the eigenvector. We know the eigenvalue is 3. And there's my eigenvector I don't know again. And although I'm very, very partial to using the first equation because it's just where my eyes look, it's probably easier to use the second equation here since there's a 0. So it's probably easier to write 1/2 times x plus 0 times y equals 3 times y, and then multiply both sides by 2 and say that x is equal to 6y, so that your vector is going to be pick y equal to 1 and get x equal to 6. You could have done it with the first equation as well. It's just sometimes it's easier to look at the second equation because there's a 0 really. Or you could have said 2x plus 6y equals 3x, subtract the 2x from both sides and gotten the same relationship, the same equation. All right, so there's my first eigenvector. Second eigenvector, A times V2 equals lambda 2 times V2. So that's going to give us 2, 6, 1/2, 0 times my eigenvector equal to negative 1 times my eigenvector. So using the first equation, because that's just how I do it, 2x plus 6y equals negative x. Subtract 2x from both sides, you get 6y equal to negative 3x. Divide by 3, you get 2y equal to negative x. So my second eigenvector is going to be, I'm going to pick x equal to 1 and get y equal to negative 2. Or you could have said negative 1, positive 2, either way. Or literally any other non-zero multiple. I know I say that all the time, but it's true. Okay, so we're almost there. To find n30, we're going to calculate p times d to the 30th power times p inverse times n naught. We're almost there. I know it seems like we still have ways to go, but we're really almost there. So here's p. P is just the matrix of eigenvectors as columns. So 6, 1, 1, negative 2. After write down P, D is immediate. D is the matrix of eigenvalues in the same order. So as we wrote V1 is our first column, our lambda 1, which was 3, should be our first column in our matrix D. So it'd be 3, 0, 0, negative 1. Right? Here's V1, there's lambda 1 in your first column. There's V2 in your second column, there's lambda 2 in your second column. This should always match up that way. And then P inverse we find by using the inverse of a matrix, of a 2x2 matrix. So P inverse is going to be 1 over the determinant of P, which is negative 12 minus 1. It's kind of gross. And then switch 6 and negative 2 and change the signs of both of those 1s to negative 1. This, not very pretty, but oh well. Sometimes matrices are not very nice. So then, yep, we do all that. It's kind of gross. So I'm looking at one thing here. Sorry, I'm looking at something. I'm feeling like I made a mistake somewhere, so I just want to make sure I didn't. 6, 1. Yeah, that's fine. Yeah, that's fine. Sorry, let me check one thing. I just don't want to blow it. Did I make a mistake here? I did. I did make a mistake. And no one should have calculated. I said y is 1 and x is negative 2, but I put them in the wrong spots there. So this vector here is incorrect. It should have been, sorry about that. So if y is 1, that should go here, and then x is negative 2. It's really easy. It's easy if you say things in the wrong order. All right, I said y first, bad call. I should have said x first. We're almost out of time here. So apologies, this p is incorrect. This p inverse is also incorrect. P really should have been in the matrix 6, 1, negative 2, 1. Sorry about that. And P inverse should be 1 over 6 minus minus 2, which is 8. And then we switch the 6 and the 1. We change the signs of those guys. Sorry, there's my correct P inverse. So finally, kind of, we're going to say that after 30 iterations of this Leslie matrix, we're going to get our P times D to the 30th times P inverse times our N naught, which is going to look like the following still terrible calculation. P, here's your matrix D, 3, 0, 0, negative 1 to the 30th power times your P inverse, which is 1, 2, negative 1, 6 times 1/8. It doesn't matter where the 1/8 goes, really. Put it all the way up in front of everything if you wanted to. Times your initial vector, which was 180. And then the multiplying out is still like not super pretty. So it's better than it could have been, but it's not great. So we multiply this out. I'm going to say, no, I'm not. So yeah, I feel like I owe it to you to multiply this out. So here's what I would do. I'm going to multiply these two matrices together first. And yeah, I am going to write it as that. So 6, negative 2, 1, 1. For this part here, we just get to write each part to the 30th power. 3 to the 30th is gigantic. Negative 1 to the 30th is 1. And then you multiply these two together, let's see, you get 100 plus 160, which is 260, and negative 100 plus 480, which is 380 times 1/8. And then we should stop because it's 2 o'clock and because I don't want to finish it. But you could multiply this out, but it's kind of gnarly because you just have this big old 3 to the 30th power sitting around. It's not cool. Next class, we'll talk about the other way to look at this. And I do think the other way to look at this is a little bit, it's a little bit nicer in some ways. So we'll talk about the other way to approach this and how it works.
It's one of the things.
Of course, which one?
I think it was like, I think it's maybe the 1913. That was that one. No. Sorry,
Okay.
I think, well, no, it's like back with the 3x3s. Sorry, yeah, I missed that.
Okay.
I stepped out.
Sure.
I stepped out for
Go ahead.
this. I wanted to see what that. I didn't get a chance to see what
Appreciate
that was. So basically, can you like give me like a brief explanation? I stepped out for like a minute.
Sure. So all we were talking about was how instead of showing something's eigenvalue, you can show something's an eigenvector by